Hello, everyone. Thank you for joining today for our Produced Water Treatment with Permanganate Products webinar with our speakers, John Sanders and Lyndon Berwick. I'm Ashley Swingle, and we will be the moderator for today's webinar. A few housekeeping items before we get started today. We are recording this meeting and everyone is kept in listen-only mode. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with your question and contact information to follow up directly after the webinar. If you are interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording within your network. Here are a few ways to find us. We have listed our website and general sales and marketing email address, as well as my email address. Do you receive our email blasts for upcoming webinars, presentations, trade shows, and technical information on our various solutions? If not, sign up on our website. You can find the Join Our Email list on any of the landing page on the right-hand side. Be sure to select the industry when signing up to ensure you receive the most targeted information for your needs. And we can't forget to mention our social media platforms. We encourage you to connect with our Carus page as well as our team members on LinkedIn, where we're often sharing upcoming events, including webinars, industry articles or news, sharing relevant posts from other industry experts, and more. Listed here is our website, and then on our page for webinars that is also on our website. And I would like to take this moment to introduce our speakers, John Sanders and Lyndon Berwick. John Sanders is the Regional Sales Manager of the Gulf region for Carus. John graduated in 1995 from Trinity University in San Antonio, Texas, with a Bachelor of Science degree in both biology and chemistry. He resides in Houston, Texas, and is a member of American Waterworks Association, American Chemistry Council, and the American Society of Sugarcane Technologists. Lyndon Berwick is a technical and field specialist with the Carus Technical Solutions Group. He has over 15 years of chemistry experience in both research and industrial sectors, including oil and gas production, environmental geochemistry, and oil field specialty chemical sales, applications, and service. He has a PhD in organic geochemical analysis and characterization. He has worked full-time research fellow with the Organic and Geochemistry Center. He was then employed as a production chemist. I will go ahead and hand it over to Mr. John Sanders.
All right, thank you, Ashley, and welcome everybody to our webinar this afternoon. The first slide, I just want to go through the outline, kind of the purpose process that we're going to go through today. To start out, we're going to go through some basic properties and reactions of permanganate just to familiarize everybody with some of the oxidation reactions that we've been studying out in the produced water treatment. Then we're going to kind of hone those into some common key performance indicators, KPIs that we see out in the produced water treatment areas. And then we're going to focus on permanganate treatment goals. What were we looking at trying to accomplish and see how successful in terms of iron removal, ORP generation, and finally some water clarification and turbidity data. And we did studies both in field testing out at actual sites, and we also acquired water from several field sites and sent it back to our lab and did some further studying that we will discuss the data later in the presentation. All of these sites were from pretty much the Permian out in West Texas, Midland, Odessa area. And then lastly, we did some comparative testing studying between permanganate and hydrogen peroxide and looked at those key treatment goals on how we compare out there with the other oxidizers. Okay. Next slide, just a basic description of what is permanganate. In chemistry terms, it can be categorized into two descriptive buckets. Manganese is a transition metal, very similar to iron. It's present in the Earth's crust. It's an essential micronutrient for life. And then permanganate is just the highly oxidized form of manganese. Next slide. And this just shows, this is kind of a permanganate's got a purple color to it. So as we look on the right, we can see as we increase the concentration on the far right, the highest concentration gets to a darker purple. When we go down the scale to a lower concentration, you get a light pink. It's still all very beneficial because you get that color indicator, so we can tell concentration, unreactive chemical, things of that nature because of the coloration that permanganate gives off. It's available in two forms. Our brand Carus, which is our potassium permanganate, is a crystalline solid, 97% or higher greater on the assay. And then it's also available as a liquid sodium permanganate. Our trade name is Carusol or Carusol C. There's two different concentrations, a 20% or 40% as pre-dissolved water solutions. So that just kind of gives you the background. The liquid has a higher solubility index, hence the 20 and 40%, whereas with the dry, it has a lower water solubility to about 3 to 5%. The next slide is going to focus on just some classic permanganate inorganic oxidation reactions, kind of go through these quickly one by one. This first one is the oxidation of soluble iron 2 to its insoluble precipitated iron 3 oxide. The next reaction is the oxidation of manganese, another common oxidation that permanganate's used for, and it's the oxidation of manganese 2 to manganese 4 precipitated out as an insoluble dioxide. The third one is showing the oxidation of arsenic 3 to arsenic 5, which can be absorbed onto hydrous manganese oxide flock and co-precipitated iron hydroxide flock, where it can be removed by clarification and filtration. And some of these phenomenon that we're talking about right here on these reactions, we're going to explain further with our data, because that was one of the benefits that we saw with our permanganate. So this will be explained how it happens out there in the field in greater detail coming up. Fourth, the rapid oxidation of reduced sulfur compounds such as hydrogen sulfide, H2S, another common reaction that we have happen out in produced water treatment. And then lastly, the oxidation neutralization of pyrophoric iron sulfide, which is a common treatment technique done a lot during refinery turnarounds or tank cleanouts. Obviously, we want to prevent that formation and get rid of the pyrophoric iron. So many times permanganate's a very common product in those situations. The next slide, we just want to focus a little bit on reaction times, the various reactions, how quickly they can occur with the application of permanganate. They can be very fast, so it can be beneficial if you have a system where you don't have a lot of time. And often when Lyndon and I have been out testing, there's been situations where there wasn't a lot of reactivity time. There were some of those concerns. With permanganate, it's generally a very quick reaction. And as you can see, with the sulfites, H2S, things of that nature, very, very quick, 1 second. It's pretty much an immediate reaction. When you look at nitrites 3, the iron 2, arsenic, it's a fast reaction, 20 seconds or less. And then we get into the dissolved sulfide manganese, it's a medium fast, so 5 minutes or less. So retention time can be shortened, and you can get a much quicker reaction, handle that loading and react quicker when we utilize permanganate. The next slide, this is just a produced water flow chart. There's many versions around. This is one we've utilized, but it kind of shows everywhere from the fracking or drilling, the well formation over to the far left. And then as we move through the process to oil water separation, gun barrel, the produced water, where it goes, and then in the purple oval with the advanced treatment, that's typically where we see these oxidizers, particularly our permanganate, where we've done it, is in this advanced treatment stage with the goal of getting the iron oxidized, removing the sulfides, increasing ORP as the water goes through the treatment and out to the pit. We want to carry out that highest ORP we can to prevent that water from going sour and developing the H2S. So this is typically the area over here to where we've studied, to where we pull out the raw incoming produced water and done a lot of our field work and the water that we use for our lab work. The next slide, this is one we've got from the Produced Water Society. Carus has also looked at, an oxidizer comparison chart, but just to quickly go through it, we're not here to do a pro and a con and downplay all of these oxidizers are very prevalent, as you guys all know, out in the oil field for produced water treatment. So just to kind of show where they all land in place, the first one with potassium permanganate, like I said, it's a solid. So if we can bring it on site and make down the solution, then we're not transporting a lot of water. So there's a benefit. It's very safe to use, as long as you don't mix with other oxidizers. But from a temperature gradient or, needing to be protected from UV, things of that nature, it's very good in absorbing that. On the cons, it can be costly. It's a higher priced oxidizer. It does have the coloration. So if you overdose, you will get, the purple or pink further downstream. And it's not as well recognized in this produced water. This is, we've been going at these studies for the last couple of years, had some people using it, but it's not as prevalent as these oxidizers down below. The other three that were listed on this, chlorine dioxide, obviously it has its pros, it has its cons. See it a lot out in the frack on the fly industry. Hydrogen peroxide, probably the most prevalent one, at least that we've run into. Obviously, very cheap product, cost effective. It does a good job at the oxidation of the iron levels, especially at lower dosages. If it's contained properly, it's fairly safe to use. But there's certain situations where you really need to utilize quite a bit of it to get the reaction all the way through to get that ORP level up. So sometimes it creates an environment to where some of these other products might be more beneficial to check out and explore. And then lastly, ozone, that's used out there. I know one particular company that uses it quite a bit, and it's also a very effective oxidizer, both with the pros and cons. Just wanted to kind of bring those out in the front. Those are a lot of the prevalent ones. Obviously, sodium hypochlorite's used in a lot of areas as well, but we didn't want to focus on every single one. KPIs, the key performance indicators, and these are generic. We realize from site to site, operator to operator, these goals change. Some can be fairly loose, some can be very, very tight. There's a big movement to try to maybe get a common KPI that's systematic and universal for everybody. I know that's been a big topic of discussion, but usually on total iron, we're looking at less than 10. A lot of them, like I said, below 2, down as close to 0 as you can get before you're sending it back. ORPs 150 to 350, although recently where Lyndon and I have been out, 300 plus is kind of the target goal, especially going out to try to maintain a very high ORP going out into the pit. Turbidities can be very low as 10 NTU, but we've also seen them at some sites where it just needs to be below 100 NTU. So big variation, and that also affects the type of treatment that you need to look at to reach those various levels. Sulfides, H2S consistently are down at 0. No H2S, they don't want that going into the pit. They don't want that going back to the frac, so that's pretty much universally at 0. pH can vary between 6 and 9, usually your standard level where your coagulants and polymers and other products work well, so we don't want to go to one extreme or the other. And then on the microbio, usually less than 100 on the ATP, but again, that can vary to 0 to I've seen some that just need to be below 1,000. So it's a site to site, operator type of issue. All right, permanganate treatment goals. We're going to go through these kind of one at a time just to show it, and then we're going to move on to talk about some actual real world testing data. But like we mentioned on the first, the oxidation of soluble iron Fe2 to insoluble Fe3, oxidize the dissolved sulfides to sulfites and sulfate, generate positive solution ORP, improve water clarification, and we're really going to get into that. That was one of our very key focuses that we wanted to look into is can we use the reaction properties that permanganate brings to improve clarification, potentially eliminate some other products, and I think the data that Lyndon will get into will show you that. And then lastly, absorb impurities onto hydrous manganese oxides, which is a byproduct of permanganate reactions. And we definitely did see this, and we'll go into detail on the data, but it's almost like a natural coagulant aid to help pull stuff out. And in many instances, it eliminated the need for an inorganic coagulant at all because of the production of the manganese dioxide. So, all right, the last one I'm going to go into, this is an example from a site that we have fed at. We real world potassium permanganate, and this, you guys that have been out to a site have seen all of these from your pre-treated or the raw water. This one at that time, 50 milligrams per liter of iron. You can obviously, it has an obvious color, a darker color, and then this just goes through the progression of the treatment chain. So we look at the iron at the post clarifier, which would be after the addition of permanganate and after the addition of your polymer, so your flocculation. So coming out of the clarifier, this site had a post filtration step, so we continue, to hold our level to where we want it. Then we go down to the pit entrance, and then finally we get the recycled water that's recycled back and sent back to the frac, and we're all the way down to 0.2 milligrams per liter. So this is pretty typical. All the sites Lyndon and I went out to have these progressions, and this is kind of what they want to see. It's usually a darker color, higher iron, higher other contaminants, down to pretty much a clean water. Most of the time, very, very low turbidities at the sites we went out to, regardless of the goal. So we want to make basically stuff that looks like drinking water and not send any impurities back to the frac. All right, so from here, we're going to transition to both the field lab testing work and some of the lab back at the Carus labs in Illinois that we did. And I'm going to pass this over to Lyndon, who, like I said, is PhD and chemist and very good at the stuff, and was heavily involved in putting together not only the data with the other scientists that did the study, but I'm going to let him walk you through all of the data and give you a better understanding of what we discovered. Lyndon?
Thank you, John. I'm going to share my screen and make sure everything's looking good. Thanks, John. Thanks, Ashley, as well. Yeah, as John said, following some of these early field observations, we wanted to take it to the lab to look in more detail at some of the chemistry that was occurring, both in field jar testing and lab experiments, and try to get some good lab data to back up what we were seeing in some of the early field applications. So we'll break it down a little. Firstly, iron removal, dissolved iron removal, that is, and then ORP, and then some of that turbidity data that we have as well. So I'm sure everyone is aware, the oxidation of soluble ferrous iron, the Fe2 form, to insoluble ferric precipitates is one of the key treatment goals, so we can avoid downstream issues with precipitation of iron in pipelines downstream and things of that nature. The graphs here show removal of soluble iron with permanganate during field jar testing at 4 different produced water facilities. There's nothing new here really, except to highlight that each site is slightly different in terms of initial iron concentrations and the oxidant demand. But in all cases, we see that the reaction occurs really rapidly, and we can achieve very low residual iron levels depending on the permanganate dose and starting iron concentration. So the next KPI parameter we want to discuss is oxidation reduction potential. ORP is a valuable parameter that can be measured easily with online or laboratory probes. In general, the treated water with an ORP above 350 millivolts is considered to be relatively free of bacteria and should have oxidized the majority of that dissolved iron that is present in the water to those insoluble precipitates that we can move with filtration and clarification. So the data I've got here compares the ORP response combined with soluble iron removal and with permanganate treatment at two different produced water facilities, 2 different sites. In both cases, we see a pretty good correlation between the 2 parameters, a rapid increase in the ORP when our soluble iron content is removed. This is not always the case for all water types, and we'll discuss this in a little more detail in the next slide. The graphs here show the ORP response at 2 different produced water facilities again, and a direct comparison of permanganate versus hydrogen peroxide. We can see a similar performance between the 2 oxidants at site 1 on the right, on the left there, sorry. But at site 2, the results with permanganate are considerably improved. For site 2, we actually repeated the test again. This was during a different sampling event several months later, and we saw the same trend. That's the final graph there on the right. So I guess the question is, why do we see this different response for different waters at different sites? Site 1 contains higher levels of both soluble and insoluble iron compared to site 2. So this may go some ways to explaining the different dose responses, but clearly the demand, the oxidant demand required to achieve a suitable ORP is not only attributed to that soluble iron oxidation. And I've got those numbers at the bottom of the screen there that you can see for total and soluble iron levels in the raw water. So there may also be an influence of organic content and composition, and also the actual nature of the organics present in the 2 waters and how those organics interact with the different types of oxidants that we apply. So we'll move on now to the next set of critical KPI parameters, which are turbidity reduction and water clarification. Some of our early site testing demonstrated how the permanganate treatment in conjunction with the polymer that the specific sites were using at the time combined to result in very high clarity and low iron water at the effluent. If we look at the permanganate half of the oxidation reaction, on the left you see the permanganate ion, which accepts 3 electrons and is reduced to its most stable form, manganese dioxide. And John has touched on this earlier a little bit. The colours here, purple and brown, are deliberate. Permanganate dissolved in water gives a pink to purple solution, as we saw earlier. The precipitated manganese dioxide flock material will be brown or black, depending on the concentration. This precipitated flock, manganese dioxide, actually plays a really important role in water treatment, not just for produced water, but for other applications as well. It helps act as a coagulant aid or seed material that is interactive with inorganic coagulants and also polymers. It helps absorb other charged impurities, particularly positively charged ions and some organics. And it also provides an active surface for the oxidation of sulfides by dissolved oxygen. So the photos here show a bit of an example of what this coagulation with manganese oxide looks like in some of our early field jar testing. The example here is with produced water using polymer only without the addition of inorganic coagulant. And we can see very clear supernatant and excellent solid settling using a fairly low dose of the oxidant, potassium permanganate. Likewise, another case study that used permanganate to treat flowback water. And again, we see that really nice solid settling and excellent supernatant clarity with the permanganate treatment without the use of the coagulant, just an inorganic, just a polymer or flocculant chemical. So following these early observations in the field, we wanted to look more closely at the advantages of manganese dioxide as a coagulation aid and verify some of the findings in the lab that we had seen in the field, and that'll be the focus over the next few slides. There's 2 key components to these studies which are tied to the key performance indicators we highlighted earlier: total ion removal, together with water clarification and turbidity reduction. The first graph here on the left shows significant removal of total ion using permanganate without the addition of any coagulant or polymer treatment chemical. And the next graph on the right again shows excellent ion removal and excellent turbidity achieved at very low permanganate dose and very low polymer doses, again without the addition of any inorganic coagulant. We can also see on the x-axis here that additional polymer doses at 5 and 15 ppm didn't achieve any further improvement in those parameters, total ion removal or turbidity. So those numbers at just 10 ppm of permanganate and 2.5 ppm of flocculant polymer were really promising.
Hey, Lyndon, can I add one thing to that?
Go ahead.
Now, I just wanted to make the point also at the site, we were able to lower the overall polymer dosage than was actually being done on the true system, and which is very characteristic in other applications with the benefits of the manganese dioxide. It kind of works synergistically with that polymer, and oftentimes you can see a reduction in the dosage of the polymer that you need to use, so you can get some back end savings that way as well. So I just wanted to bring that point up. I think the jar testing, we were able to go half the dose and still get very excellent results.
Yep, exactly, John. And we see that again in these next few slides as well, where with a direct comparison with the peroxide. So yeah, as John mentioned, the next focus for us was to look at a performance comparison between hydrogen peroxide, one of the most commonly used oxidants in the produced water treatment. Compare that with permanganate and look at these two parameters, total ion removal and clarification. So the data here from site 1 shows total ion removal with the addition of an anionic polymer on its own, and also then the same polymer combined with an inorganic coagulant as well. In this case, the coagulant was Pacl polyaluminum chloride, which is fairly commonly used. Again, for this site 1, we observed pretty similar performance for permanganate and peroxide when we applied the 3 treatment chemical strategy. So that is the second and the fourth data columns here. You see fairly similar, almost identical total ion removal. But if we then compare the 2 oxidants using polymer only, the data columns 1 and 3, we see much more improved performance with the permanganate. And again, as John touched on, another important factor here is that the polymer dose with permanganate was half that we used for peroxide. So for this particular site, you would say, okay, fairly equivalent results. But if we move ahead to the second site that we looked at, this one here, the same test data, again, total ion removal, really significantly improved performance for permanganate against peroxide, both with and without coagulant addition, and especially using just the 2 product strategy using polymer only, which I've highlighted here. So we can see total ion really not being removed much at all with peroxide and polymer only, but down to very low levels with permanganate and polymer. So again, we sort of talked about this during with the ORP data. Why is there a difference between the 2 sites, and is what's actually occurring? The main difference between sites 1 and 2 is in the distribution of the ion between soluble and insoluble phases, and so therefore the total solids content. Site 1 has a higher total ion, a larger amount of already precipitated solids, and so we see fairly similar solids removal with the 2 oxidant treatments. On the other hand, with site 2, it has a much lower starting total ion content, and so we see poorer settling performance using peroxide because of that lack of additional manganese dioxide flock that is provided with the permanganate treatment. So the next 2 slides are basically the same comparison of permanganate with peroxide for sites 1 and 2. This time though, we're looking at turbidity as a measurement of water clarification. As most of you I'm sure are aware, turbidity is a general measure for the level of total suspended solids, and like ORP can be done easily with online probes or laboratory instruments. For site 1 here, there is a similar trend to what we observed with total ion removal. Fairly comparable performance for peroxide and permanganate in combination with the inorganic coagulant and polymer. Again, note that the turbidity of the untreated raw water here is very high, so that helps that natural flocculation and solid settling. But again, the polymer dose required with permanganate was half that required for peroxide. Moving back now to site 2 though, we again see vastly improved performance with permanganate. The treatment with peroxide resulted in only minor reduction in turbidity, starting turbidity of 119 and even with a 3-product program of peroxide, Packle, and polymer, still pretty poor turbidity numbers in this supernatant. But permanganate, we get excellent numbers, both below 10 NTU, both with polymer only or with the addition of the coagulant. And again, this can be attributed to the presence of the manganese oxide flock produced as part of the oxidation reaction with permanganate. For raw waters like this one at site 2 with low iron content, this is obviously really advantageous and eliminates that need for inorganic coagulants. So to finish up here, a brief summary of hopefully the important takeaways from this presentation. Permanganate is a strong, stable oxidizing agent used extensively in water and wastewater treatment. It's added to produce water as a first chemical treatment step ahead of clarification or filtration, and reacts very rapidly to remove soluble iron, increase ORP, and improve water clarity. It can provide similar or improved ORP results to peroxide at equivalent dose rates and lower. And really the most important thing, I think, the manganese dioxide byproduct of permanganate treatment really is an excellent coagulation aid. It can eliminate the requirement for the addition of inorganic coagulants and also reduce the required doses of polymers or flocculants, effectively allowing a 2-product program of oxidant and polymer instead of a 3-product program. And finally, permanganate can also help provide more consistent treatment efficiency and performance for variable raw water types. So if you've got differing incoming TSS or total iron, dissolved iron levels, you've got a bit more wiggle room if you're applying permanganate. If you've got different wells coming online and that character of that raw water changes, your permanganate treatment will provide more of a stable treatment performance and efficiency. Thanks everyone for listening in. I'll throw back to you, I guess, Ashley, for questions and comments.
Yes, thank you, John and Lyndon. Listed here are their contact information, so feel free to reach out to them. We did receive a question. How do you handle the solids, disposal, waste costs, etc.?
I guess that depends on the facility itself. Of course, there's going to be more solids when you're applying permanganate. If you've got a DAF unit, you will more than likely generate more sludge. If it's an aerated settling tank, again, you'll have more sludge. It depends on the facility itself and how that is managed. John, do you have additional comments?
No, I would agree with that. From the facilities that we've done and utilized it, it hasn't been an inconvenience or a major issue. But yeah, if you're talking a very, very super high dose of permanganate and generating a lot of solids, then yes, you would need to have an extensive solids management program, and you're going to have more solids to deal with. But at the levels we did this testing and kind of the NIT solid, cost competitive, all of that treatment levels, I don't think the solid generation is an excessive major issue.
No, and if you're eliminating the addition of an inorganic coagulant, right, it's sort of like for like there. So manganese dioxide becomes your coagulant. So it's sort of a similar generation, solids generation.
Exactly. And then I just want to add one more thing. For future studies, we didn't put a real slide, but our goal is to continue to explore permanganate and where these secondary benefits are. We think the elimination of inorganic coagulants, the purity that it does to the water, and the ability to clean it up with the natural coagulant aid is definitely a benefit. But we need to continue to look at that across all types of waters, different basins, evaluate full trial systems, not just jar testing results and laboratory study results, but let's look at real world on various pieces of equipment from DAFs to clarifiers to just open settling tanks, to continue to evaluate where our secondary and tertiary benefits lie, because we know they're there, but we need to continue to look at that to see how permanganate can differentiate itself, and those are definitely in our plans.
Exactly, and also another key one I think we're looking at in the near future is that ORP stability. How can we maintain that downstream relative to some of these other oxidizers? And I think that's another benefit that we can have with permanganate, just to get those higher initial levels and maintain that stability and bacteria control and downstream in the pit, and then in injection into the frac or re-injection.
Okay, and we had another question come in. Did you have any issues with treating low alkalinity water?
We didn't measure alkalinity, but I mean, the permanganate is fairly versatile, though. That ideal reaction occurs within a pH range of 3 to 9, 3 to 10. So there shouldn't be a major issue in that regard.
Perfect. Okay, well, if anyone does come up with any further questions, feel free to reach out to either of them with the contact info shown on your screen. Other than that, thank you, John and Lyndon, for the presentation, and thank you everyone for joining today. Have a great day.
Thank you, Ashley. Thanks, John. Thanks, everyone.
Thanks, Lyndon. Thanks, Ashley. Y'all have a great day. Thanks for attending.